The at-rest state of the environment relative to the Schumann resonances acts like an elastic that wants to come back into its at-rest state. All right. All right. So this is a part 2. I had another video I was working on. I hit the wrong button. I stopped it. And so I'm kind of picking up in the middle of my presentation. All right. So I'm not sure what I'm going to do with this. I have 2 parts. I don't know if I'm going to edit it or whatever. All right. So let me move on because this was really, that was a little disconcerting and it was a little frustrating to me that I had moved on forward in the discussion and now I got to go back and retrace my steps, and I'm kind of not really happy about that. So that's where I am right now. Okay, it's talking about the at-rest state of the canvas, and I'm trying to pull myself back to be at the at-rest state of me. Okay. All right, the field of action moves, the antenna detector wires. All right, let me look what we got. All right, so the field of action moves, the antenna detects a signal coming from top down or bottom up. All right, top down is amplitude, bottom up is the magnetics. All right, magnetics move bottom up. Our at-rest canvas, or the field of action, may be acted upon by amplitude strikes or by magnetic waves that have traveled around the world. The at-rest state refers to a state of balance, which is acting against the influences of the immediate environment. So the immediate environment is what's coming to the antenna detector wires from around it. The immediate environment is what is near the Schumann antenna, the Schumann resonance antenna, for it to pick up. It can't pick up something miles and miles away, right? It doesn't have that capacity. It's a passive receptor that only what comes to it, it's going to tell you about. So if there's something that's happening way, way, way off in the galaxy, like with another planet, it may not be picking it up. Okay. The magnetic waves travel around the world. The at-rest state refers to a state of balance acting against the influences of the immediate environment, like I said. So when I talk about the Schumann resonances, I make it a point to say always know what's happening locally on the scene before you start saying that something happening with the rest of the world. You need to look locally at what's happening around the antenna detector units. Okay. At Tomsk, Russia, the SOS, which is Space Observing System, that's the people in charge of the actually running the operations of the antenna, the SOS, uses both an amplitude detector and the magnetic side detectors. As such, we receive both types of signals, top down and bottom up. The at-rest canvas may get colored from the top down through amplitude or bottom up through magnetics. Now that we are ready to start detecting a signal and our canvas is theoretically ready to be painted on, what are we using for our palette of colors? Correcting what I wrote here. Okay. So I've laid the scenario out and why I'm talking about painting. Why this is so why the analogy of painting is so important is because we're starting with a at-rest state, a canvas of an elastic canvas that responds to the environment. All right. So it's that is always in flux. Whenever the antenna picks up a signal, it's going a signal from the environment. It is going to relay that information out to the processor that sends it out to the spectrogram. All right. So within the scope of the wavelengths that it's measuring, you have various size brushes that get detected. Okay, various modes. It's like on a microscope. You have the different power settings times x, x10, x100, X1000. All right. That's kind of what these modes are. That's the way to look at the modes, is it's different portions of the same exact signal. Okay. There's one continuum, one spectrum of the Schumann resonance signals that get detected in various wavelengths depending on the mathematics of the size and the shape of the tool that they're using, the brush. When I say the tool, I mean the brush that we're using to paint our picture. And we're using to paint this wonderful abstract art here. How are we doing that? How are we painting this picture? Is with the different size and shapes of the brush. Again, this is an electronic determination of what's going on in the environment. This is not that, where am I? That over there is not the Schumann resonances, okay? This right here is a representation of something that's invisible. It's not colored white, it's not colored green, it's not colored yellow. Those are arbitrary colorings. So what I'm trying to explain is how they're getting this representation of what's happening in the environment using the colors. Okay, they're using colors to express and describe different wavelengths of signal that are happening around the world, that are coming in at different times, and they're coming in at different heights. And there's lots of different frequencies and intensities that are involved here. And it is the job of the spectrogram to break it down using the different types of brushes, like I said, the different types of tools, so that you can understand it in colors rather than abstract frequencies. Right. Okay, so in the all right. So this is when I talk about the brush, when I talk about the canvas, this is what I'm talking about, is getting this signal here to come across through the different, getting that signal to be represented using colors to represent different wavelengths, strengths, and intensities of the signal. Okay. If you were, for example, if you were to look at an ocean, you see different colored blues, you see a darker blue. It depends on the depth that you're going in. And if you're looking at the color of the ocean, for example, you're seeing a dark blue, a lighter blue, a greenish blue. You can tell there's various things going on by those colors. This is similar to that, but the coloring here is arbitrary, and it's not based on the physics of the water. That this is based on mathematical computations saying that the wavelength is X size. So based on that parameter, what's in this box, we will color it green. Okay, so that is why this is not like the ocean or not like the water, where you can't look at it and see, okay, the water here is darker, so it's deeper. There's not a physical correlation between the color here on the spectrogram and what's actually happening, because the waves are invisible. They don't have a color. The Schumann resonance waves are invisible. They don't have a color. They certainly don't have white. They're certainly not green. So what they've done is they've artificially colored the mathematical model for the size of the waves, but it is not, the color of the wave is not green. Right? It's not a one-to-one correlation. It's not a, like the ocean where, again, the ocean where you see a darker blue means it's more of a density. That's not quite what it is here. That's not here how that is designed. That's not engineered this way. It just so happened the sky is blue. It just so happens this here color is blue. I don't know how much that was intentional to do that. I don't know if the engineers had ever intended that to be looked at as, well, the sky is blue, so let's color this blue. You know, to me, it seems, I mean, it's not beyond the range of reason. I don't believe that's why that this is a blue color, to tell you the truth. This is a blue color based on the fact that, again, the dark blue is easy to work with. It is not because the sky is blue that they started out with a blue color here. Okay, I saw that one place, maybe two places where people assume they believe that this is like photorealism of the environment, that they see, well, the air is blue, so this is blue, so obviously that's what it is. No, the coloring of the blue here is a arbitrary choice, but it is based on the needs of the chart being able to tell you accurately what's happening, and not the fact that the sky is blue. That's a really important thing to point out to people. Okay, so we have our colors set. I'm sorry, we have our canvas set with the color blue, dark blue. That's what we're starting with. Our four primary colors that we're working with and doing our painting here are white, yellow, red, and green. Okay, so these are, once again, they're more arbitrarily picked out. I don't know why they picked out these colors other than they're primary colors and they can stand up against each other. Okay. So the primary colors that we're using for our painting, for our canvas, are white, yellow, red, and green. Each color represents a mode. Mode colors are, the white is 1, yellow is 2, red is 3, green is 4, and this is for Tomsk. We see the numbers on the graph strips coming from Tomsk, A1, A2, A3, A4. What does this mean? All right, so I described that earlier, that this here, A1 is amplitude 1, A2 is amplitude 2, A3 is amplitude mode 3, A4 is amplitude mode 4. 3 and 4. All right. All right. So the best way to see, as far as I know, relative to what I'm trying to teach, the best way to see the modes is relative to a canvas and a painting analogy. If you see the modes as different size and shape instruments, if you're familiar with brushes and with paints and calligraphy pens, then you have a basic idea of what we're talking about. The theoretical painting is photorealism. We are representing actual events in real time as they occur. This is called plotting. The amplitude and height. The amplitude is height. The magnetic strength and direction is the quality, which is the long way. Incoming signals, which are electromagnetic radio frequency waves, is plotted using the tools of the modes to draft a spectrogram of the signal. Okay. The modes, as represented by colors, are plotted using the numbered modes representing a size and shape of the EMF information below 40. All right, so Tomsk truncates her information at 40 hertz. Okay. I'm going to get into this a little bit more later. Okay. The modes represented by colors are plotted using which represent the size and shape of the EMF wave. Okay. The modes are based on the fundamental frequency as representing the first mode. All right. So the first fundamental frequency is 8 hertz, or in our harmonics, it's 7.8. So this is the first mode. 7.8 is our first mode. The modes are based on the fundamental frequency, which is 8 hertz. Okay. I'm going to, at this point, completely baffle the reader with a definition of Wikipedia, which should clarify nothing. It should do all of clarifying nothing, but I don't think this minor inconvenience should stop me. Okay, so I'm going to pause here so I can have a drink. A mode. What are the modes? A mode of vibration is characterized by modal frequency and a modal shape. Okay. Actually, I am going to pause this here. Hold on. Okay, I'm back. All right. So we are talking about, we're not just talking about modes of the waves. We're talking about standing waves. Okay. And so that's why I have this kind of picture up here, so you can get a picture of the modes relative to standing waves of what we're talking about. So I will read to you what it says from, this is from a journal from Wikipedia. In fact, I think this, where I got this from, is originally this article here, somewhere in the midst of the text. Okay, so a mode of vibration is characterized by a modal frequency and a mode shape. It is numbered according to the number of half waves in the vibration. For example, if a vibrating beam with both ends pinned displayed a mode shape of half of the sine wave, which is one peak on the vibrating beam, it would be vibrating in mode 1. If it had a full sine wave, one peak and one trough, it would be vibrating in mode 2. In a system with two or more dimensions, such as a pictured disk, all right, let me find the pictured disk. All right. Okay, so this here, pictured disk. All right. Such as a pictured disk. Each dimension is given a mode number. Actually, can we? All right. All right, so it says vibration of a single normal mode in a circular disk with a pinned boundary condition along the entire outer edge. And this is giving you, like this is a drum head that they're giving you a picture of, but they're calling it, this is the pictured disk. All right. Using polar coordinates, we have a radial coordinate and an angular coordinate. If one measured from the center outward along the radial coordinate, one would encounter a full wave. So the mode number in the radial direction is 2. So the radial direction is moving outward like that. Okay? The other direction is trickier, as if this isn't tricky enough, because only half of the disk is considered due to the anti-symmetric, also called skew symmetry nature of a disk's vibration in the angular direction. Okay, you're following all that. Thus, measuring, okay, hold on. Thus, measuring 180 degrees along the angular direction, you would encounter a half wave. So the mode number of the angular direction is 1. So the mode number of the system is 2, 1 or 1, 2. Okay? Depending on which coordinate is considered the first and which is considered the second coordinate. So it is important to always indicate which mode number matches with each coordinate direction. Okay, so when we're talking about a coordinate direction, we're not just talking about that. All right, we're talking about the coordinate direction, meaning you have, actually, let me see, hold on, let me see if I can get the better picture. Okay, so when we're figuring out the mode number, and therefore which color, we talk about the coordinate. All right, what I was just saying here, you talk about the, but it's always important to always indicate which mode number matches with each coordinate direction. So a coordinate direction is either along this line, this is your standing wave, this, the height of it, okay, where we're talking about this here, the height of it, this is your amplitude. So the mode, what they're giving you, they're stacking it up here. So this green one here, which matches the green of the Schumann that we have, okay, that's, they're giving you T1 as the height here. All right, so this is yellow, T2, T3, T4. All right, so this is amplitude because it's giving you the direction, the coordinate direction of up, or height, or vertical. Okay, that's what this is giving you here. The modes of the height of it. You see the height, and the height, the amplitude. All right, these are modes of the amplitude. This here, okay, is giving you the modes of the magnetics. Okay, it's like a string. When we talk about the when I talk about the Schumann resonances, hold on. Okay, so when I talk about polar coordinates and I talk about the modes, okay, let me see if I can get this in. All right, so when I talk about the polar coordinates and I talk about the modes, this is what I'm talking about. We have these are the modes of amplitude. Okay, that's this right here, the height. And then over here, we talk about the partials on a string. That is relating to our magnetics. This is the quality portion of the program. So we have, when we talk about the modes, we talk about getting them in reference to the polar coordinate. We have the amplitude as the height, that's vertical. Okay, here, that's vertical. Okay, and then this over here is the horizontal. Okay. All right. So where was I? All right. So this is generally speaking, what I've read so far. This is the first part of it, where it's talking about the modes, is getting it in terms of the coordinate of what you're looking at. Whether you're looking at it from the amplitude, the height, the mode of the amplitude, or the mode of the of the harmonics. And what you're seeing here on the Schumann resonances is both of those. You're seeing both of those polar coordinates plotted here on the spectrogram. And so that's why it's difficult for people to look at this and understand that we're talking about two different directions that things could move in. All right. Even though you're looking at it's all the environment, there's the electric side, that's the amplitude, the electric side, that's one polar coordinate. And the magnetics moving this way is the other polar coordinates. So what it talks about when it talks about the 2 to 1 or 1 to 2, it's talking about going one way. The amplitude is tall and narrow. Okay, the amplitude is a tall and narrow signal, whereas the harmonics, the magnetics, are short and fat. So the two different size brushes, two different configuration brushes, are either narrow and tall, skinny and tall, or short and fat. So those are the directions, those are the modes, those are how they create the pictures here, is by the size and the shape of the tool that they're using to paint on here. Okay. Hopefully this is making some sense to someone. All right. So the mode number of the system 2 or 1 or 1 to 2 depends on which coordinate is considered the first and which is considered the second or the third or the fourth. We're talking about Tomsk has 4 modes and not just 2. In linear systems, each mode is entirely independent of all other modes. In general, all modes have different frequencies, with lower modes having lower frequencies and different mode shapes. So they're independent of the modes in that direction, but you still need to line up which polar coordinate are you measuring. Is this the modes of amplitude, or is it the modes of magnitude? I'm sorry, magnetics. Which quality? Okay. Is it measuring the amplitude, modes in amplitude, or is it measuring the modes in magnetic? All right. So that's where we have the wave interference, is this one here. Actually, let me see if I can pull up that. Hold on, let me pause this. All right. So in my notes, that's where this picture takes place. All right. So I'll let you kind of check this out for a minute or two. And this is what we call this is the wave interference GIF. All right. So this is talking about the modes of interference of the waves. All right. So you're looking at relative to the all right. So the height, it's going up the height. All right. So this is mode 1. See this way up here, mode 1. Boop. It moves, goes back and forth. So this is mode 1. This height that they're at there is 2. This is mode 3. And this is mode 4. All right. Did you get that? The height of an amplitude, the height of it is this. That's mode 1. Then this point here, that's mode 2. That point there is mode 3. And then the bottom of it is mode 4. all right, relative to the amplitude. Okay. That's a great picture. I love that picture. All right. What else we got? Oh, come on. Okay. Okay. All right. So that's a standing wave interference. All right. In physics, a standing wave, also known as a stationary wave, is a wave which oscillates in time, but whose peak amplitude profile does not move in space. Okay. So you're seeing that? Actually, hold on. Oop. Okay. It does not move in space. The peak amplitude, all right, so that's what a standing wave is. That it vibrates in place, basically. It's not rolling, it's not propagating, it is standing in place. That's what the Schumann resonances are standing waves that fluctuate in place. They don't roll along. The peak amplitude of the wave oscillates at any point in space. All right, let me read that again. The peak amplitude of the wave oscillations at any point in space is consistent with time, and the oscillations at different points throughout the wave are in phase. The locations at which the absolute value of the amplitude is minimal are called nodes, and the locations where the absolute value of the amplitude is maximum are called antinodes. All right, so you see this is what it's talking about here, the nodes and the antinodes. So at its height, that's a node, and when it's at its bottom, the absolute value of the amplitude is maximum is called the antinode. Okay, so I guess up here this is the antinode, and the bottom of it is the node. All right, if I read that correctly. A standing wave is a continuous form of normal mode. In a standing wave, all the space elements, for example, x, y, and z coordinate, are oscillating in the same frequency and in phase, which means they're reaching an equilibrium point together, but each has a different amplitude. Okay? All right, so we're following along with that. All right. The fundamental and the first 6 overtones. All right, so I have given, all right, so this is the first 4 overtones. All right, so when we're talking about the modes of amplitude, we're breaking it up like this is, so depending on the polar coordinate, your mode can be moving from bottom to up, or it can be moving from top down, all right, as it were, here in our illustration. Okay, so the height, the amplitude, the height of it, the I guess the antinode measures the maximum peak frequency that it's reaching for that particular moment. So the node is your height in amplitude right there, or the antinode, I'm sorry. The antinode reaches a height and amplitude. So this right here, that peak right there would be your node, and then this is your antinode, I guess, apparently, from what I just read there. So, um, so we're looking at the different portions of the signal, different wavelengths, different strengths, as giving you the different intensities, different colors of the modes. All right. Okay. So that is that all that I just read. That ends the quote from Wikipedia talking about the normal mode. All right. All right, so back to my text. All right, so the 12 dependencies. All right, so this is where we start getting into what's kind of really the nuts and bolts of Tomsk, the Tomask Observatory. See if I can get there. Yeah. The next section here explains the use of the modes is difficult without numbers and specific technical data. I have some of that on the board here when we talk about Tomsk, but overall, really, honestly speaking, you see the numbers here. All right, and if I go, let me give you the numbers. All right, so the numbers here tell an actual story. Okay. Our high point here, this is today, our high point here is 43, okay? Then the next one up is 22. And you see the next one up is 14. And you see the next one is 10.5. Okay. So these are like nested in each other. Okay. They're nested within each other. It's one continuous, it's not a wave. This is amplitude. Amplitudes are not waves. But this is one solid wave that's coming at you of material, of electric. Okay. It's not a wave, it's like a wall, I guess. Hard to explain it. But this is the initial burst that comes to us. You see these peaks here, the synchronous mode peak. It starts at almost nothing, boom, and the nothing of the chart, which is nothing there being 2, the baseline of 2. See that? It's very little. All right, 2, 10. All right, so our baseline of where we go is 2 to 10. And then from 10, it shoots up to 43, then drops down, peaks up, then drops back down to 2. Okay, so our C state right there, this is the baseline that we're going by is this 2, and these are pico electron volts, by the way. So this is like a wall. This is a big kind of wave of amplitude that's coming at you, but it's upright. It's not a wave like that, like the other part of it. This is coming at you dead on like that, like a truck, if you will, coming right down the line at you. All right. So the height, so what this is measuring, this white is measuring the height of the signal. Okay. There's also these other color modes that are included as well. These two together give you orange. Okay. The yellow and red give you orange. Red and green give you a maroon color. Okay. And the white and yellow give you white. White by itself gives you white. White and yellow gives you white. Okay. Relative to the Schumann resonances. Okay. So this is, again, this is amplitude. This is measuring the height of the signal. This is mode 1, mode 2, mode 3, mode 4. Okay. We see the modes as, all right, let's go on. What does it say? To balance the need for technical and scientific data with overall readability. All right, so I'm not giving you too many of the numbers. I am giving you some specific numbers here because I'm reading what it says here, but I'm not focusing too much on the numbers themselves because I want you to understand what you're looking at before we focus on what the numbers actually are. Is this number a good value? Is it number good value? People ask that all the time. And it's like, well, let me tell you what you're looking at, and you can tell for yourself if it's a good number. And in reading the charts of the Schumann, let me just say, no one can tell for you if it's a good number. People want to, they want to tell you, they want to give you the information, they know, they want to share it, and that's fine. But each person is receiving this and responding to these waves in a little different fashion than each other. So there are similarities, but it's more important for you to kind of know for yourself what it's doing rather than someone else telling you, oh, is this a good number or a bad number? Chances are they don't know. Right? Who knows how long they've been looking at it? You have to determine for yourself. The only way you can do that is to know what you're reading before getting into any specific numbers. Okay, even though you have numbers, the numbers are up there. It's more important for you to know what you're looking at relative to how it's all put together as opposed to what any particular value means. Like the answer to 2 plus 2 is 4. You know, that's what a lot of people want. Oh, just tell me what I need to know and and then I'll do it myself. Well, I can't do that. No one can do that. Surprise. The people that are telling you what it is, maybe they don't really know. That's why it's important for you to know. That's what this whole journey is you finding out for yourself what these values mean. And not going by what someone else says, whether a 36 number on here was a good number or a bad number. I saw that there was a comment on the Facebook page where someone had said that, where the number given was 36, which if you've been here for a while, 36 on the amplitude is low. And someone said, oh, that's great job, we did it. And then the newcomer was commenting, what did we do? Is 36 a good number? What is a good number? What did we do? And my response to that is, I don't know what that person did. I don't know what they know or what they think, but 36 is a low number on the amplitude. It's relatively low, especially if it's the white number, the peak, because you also have the other numbers as well. You have 40, today is 43, then you have 22, then you have 14, and then you have 10, 5, 10 and a half. So each one of these numbers plays a role in what you're getting. It's not just the one value of the white. There is also the other modes that are important that are also sending out information as well. And sometimes the other modes have more going on than just the white mode of the high peak of the amplitude. Here at Tomsk, that's what this represents. The white is the high peak, the high mountain peak of the amplitude, but there is other stuff underneath it that you really need to understand. The yellow, the red, what you're looking at up here when you get orange. What does that mean? What is that? What's that orange? And the green, what is the green as well? Okay, so I tell you, I explain what you're looking at with the colors relative to the Schumann uh, diagram based on this kind of model of a painting and the brushes, if you will, if that makes a lot of sense. We're painting with electricity. You know, just because you're not seeing something underneath this white doesn't mean there's not something there. That's why I'm pointing this out. That's why we're doing this. That's why this is important. This is not, people use that expression, whiteout. That's not what this is. If you're talking to me, please don't ever use that expression, whiteout, unless it's snowing outside and you can't see out your window. Right? That's what whiteout is. When it's snowing, it's a blizzard and you can't see out your window. That whiteout, the whiteout does not apply in any way to the Schumann resonances. And the more people use that, the more I'm just going to say that to you. That's just some phrase someone threw out to you, and it doesn't mean anything. Calling it a whiteout condition of the Schumann is reinforcing bad information that led you off track, and you're repeating bad information. This is not a whiteout because you have, again, the 22, you have the 14, and then you have the 10.5. This is right here. This is right underneath it. Where are you getting your information that says this is a whiteout condition? I will tell you where I'm getting my information that says it's not a whiteout condition. You don't have to prove anything. I don't have to prove anything either. However, if you're going to use terms, please use them correctly, right? It's simple. If you're going to describe what's on there, please use it properly. Please use the terms properly. And if you stick with me and you follow along with what I'm saying, you will be able to, you'll have a good understanding of what's happening, and it won't just be the gibberish of 5D gamma energy, whiteout conditions, flatline, all these what do you call it? Jargon, right? The ascension seeker, ascension age jargon of the Schumann resonances. It's a lot of it is around us, and that's what I'm here to dissuade you from, is using more of the ascension age gibberish that people throw out at you. That they don't know what it means, and they'll try and explain it, and you'll listen and look, and you read it, and it's just confusing. Okay. So the white here, this white condition, is the height of the amplitude, and it is not the whiteout condition, as some people would want you to believe. It's not a whiteout condition of the Schumann resonances. Okay. All right. So we see the modes as bandwidths, which are separations of the entire spectrum. In other words, it's a means of breaking down the entire spectrum into EMF, manageable pieces of the EMF spectrum. All right, so white is mode 1. It correlates with the highest layer of the ionosphere, furthest away from the planet, highest frequency of the lowest range energy where the resonances reside. All right, so when I say where the resonances reside, that means the Earth itself. So a lot of the amplitude waves are actually, how do I say this, are actually higher in the atmosphere than people are. I think that's a good way to put it. When you get those whiteout days, that's higher, according to what I understand. The 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 white conditions are traveling up higher in the ionosphere. And I will say people who live on an elevation, Colorado, mile up, you're more likely to be affected by those, the high amplitude, than you are than I am here at sea level. All right. The position on the globe matters for where you're getting the most out of these the white caps, what I'll call the white caps. So depending on where you are, you may not feel them as much as other people on the globe. Okay, the amplitude moves in a straight line. It's vertical, moves in a straight line, and um, that's what these shapes on the Schumann resonance are. Is they are the vertical amplitude portion of the signal that's coming out. Okay. So when I say it's when I say it's lower energy where you reside, because the amplitude moves top down, ding, 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 comes top down. So the high point of the amplitude is up higher. Okay, that's the best way to kind of look at this. This is a general condition of the Schumann resonances, that the higher the energy is coming from, the less uh, noticeable or the less effect it has down at the surface. I think that's a good way to put it. You have the initial discharge, which can oftentimes blow a hole. Okay, that's localized to that one spot. Okay, so an amplitude strike coming down, boom, blows a hole in the earth. Okay, strong power, boom, that's localized to right there. But then as a result of that, it sends out energies. Okay, sends out radiations from that, which are not as strong as the initial spike of amplitude. And as far as I know, in all cases, the amplitude coming down is going to decrease as it moves through layers of the atmosphere. All right, so it leaches off after the initial discharge, it leaches off charge from the first spike, which it leaches off into current as magnetics. So as it's no longer going up and down or down, and it's discharging into the atmosphere, that turns into current, which is the magnetic side. All right, so mode 1 is the highest, the tallest. Mode 2, the yellow, is lesser in height, lesser in amplitude. The red is mode 3, lesser in amplitude, lesser in height than 1. And green is mode 4. It's the lowest frequency, it's the lowest in wavelength, but it is the greatest in intensity because it is the biggest wavelengths that are there. Okay. All right, so plotting the spectrogram. Okay. Due to the abilities of the antenna to pick up only certain signals, these colors are going to appear in certain recognizable patterns based upon the type of signal, whether it's more electric or more magnetic. For example, the bright green shows up largely as bands due to the fact that it is exhibiting the characteristic of the magnetic waves. Okay, depending on where and how the EMF signal interacts with the antenna, this is the type of mark which is going to be plotted on the spectrogram effectively. All right, so if it's a quick jolt, there's just going to be a line. All right, discharge, essentially discharge from the ionosphere to the ground shows up as a line, boom, real simple, quick and easy. It's there, it's there, it does its job, and it moves on. Quick, hot and heavy, quick, fast, boom, and then it goes. Then what you're left with after that are the magnetics. So these spikes here, you see these periodic spikes, just really quick, bing, these are amplitude, spikes of amplitude. See this one in green? Bing, measures, and these right here, again, spikes of amplitude. So you see, when I say there's a correlation between the signal shape and what's happening on the spectrogram, you see it kind of comes in quickly, and then it peaks. See that? Comes in quickly, dink, then it peaks, goes back up, then it goes back down rather rapidly. So this spike here is an amplitude wave, which you're seeing right here. So that's what I'm saying. They equalize each other out. The size and shape of the wave will appear on the Schumann spectrogram. Likewise, these are magnetics, and these are coming at you this way. Remember, this way. Okay. So the quality rating, okay, would appear as a horizontal band. Okay, so you'd see this, a white, you'd expect to see a white in the band here, or lesser of the green. Okay, so you're getting, and this is interesting, getting in this particular one here, all right, what you're seeing is this yellow and red together equal orange. All right, see this right here, this is a low number, 8.3 in the magnetics, this is a low number. This right here is 17, that's a higher number. This right here, the red, is 52. Gets this point of 52. Red and yellow together equal orange. Okay, remember that. So you have these numbers. So amplitude is a high number. You get these high peaks. The high spikes and peaks of amplitude mode 1 are here. You get the white of that. Okay, it's not the same way with this. This white number is low compared to the other ones here. That's why you're not seeing in the middle of this a white band. Okay, you're seeing orange because look at these numbers. It's 52. The peak of that is 52. Most of it's in like the 14, 12, 14, 20 range. So these two together, the yellow and the red, are equaling orange. Okay, so these ones here are appearing out from heart to heart. Well, that's the magnetics from heart to heart. And that's why you're getting this orange color. And that's why there's no white there, is because the quality, on the quality, the value of the white is only 8.3. It's tiny relative to 17, relative to 52. Okay, so again, the amplitude spikes up like that. The quality, which of the magnetics go horizontally. So the quality bands you're going to see as big fat bands. It's not going to show up as spikes. This doesn't show up as spikes. This shows up as a stronger color in the middle of this horizontal band. These horizontal bands are the actual Schumann resonances. These are the harmonics, and these are not the electrics or the amplitude. Okay. In other words, white and yellow frequently appear as spikes or vertical lines due to high current of electric charge, and the fact that this is how the antenna picks up those signals. So you're looking at the height of these numbers, 43 and 22. So you're going to see this as white because it's white and yellow. It's primarily white and yellow. That's what's picking these up. But it's not, you're only seeing behind it, behind this white, you're seeing behind this white, you're seeing the orange and the red, okay? So when you see it fringed with rust and orange, it's not a whiteout condition, all right? It's just a white peak. It's a white spike. This is not 5D gamma energy. This is not white light. This is not incoming from Alpha Centauri or whatever, you know, especially when you get a 43. That's not an incoming into the Earth's, you know, sphere number. Okay, I'll just say that. 43 is a relatively low spike. You see it peaked up here. Oh my God, it's peaking, but this is not hertz. This is your decibel scale. This is just simply measuring the intensity of the signal. It is not the frequency of the signal. So in other words, the Schumann resonances did not go up to 43. However, right, because that's an amplitude spike is at 43. This right here This is at 37, and this is at approximately 33. These are the Schumann resonances here. These horizontals, these are the Schumann resonances. The horizontals that I'm kind of stroking nice and gently here, that's what these are. The spikes of amplitude are like taking and hitting the bell. Ting. Hitting the bell is not the ringing of the bell, is not the vibration of the bell. However, you couldn't have the ringing bell without hitting it, right? I mean, you hit the bell a few times and it rings, it rings, it rings. And then when you want the bell to start all over again, you ring it some more, okay? And so that's the interchange of what these are. This is like I said, if you take the Earth and look at it as a bell and you hit it with these electric spikes, what you have left are the Schumann resonances. And again, Professor Schumann, when he first talked about first talked about those, he described them as the ringing of a bell of the atmosphere. All right. So that's what we're talking about of the Schumann resonances here are the ringing of the bell of these guys here. Okay. And not the incoming spikes, which are periodic. You see, it's fine for a while. In fact, you look at this. This is interesting. So this is 1, 0, 1. All right, so this is midnight, 1, 2, 3 in the morning. So that's roughly the middle of the day here. Okay, we are 7 and 5. I'm pretty sure it's 7 and 5 or 7 and 6. So that's 13 or 14. I'm where I am in America. I'm halfway around the world from these guys. So that's approximately 12 hours away. So so during this time in the middle of the day, approximately 1 or 2 in the afternoon, that's when this energy came in here. Okay. All right. All right. So white and yellow modes are heavily in electric, usually. Red and green modes measure the layers closer to the Earth. Green measures the layer of EMF waves which occupy the space between the Earth and the lowest layer of the ionosphere. Ultimately, the ionosphere. I wrote illosphere. Ultimately, the ionosphere acts as a filter of sorts, which forces the bouncing or return characteristics of the various I wrote that crazy. Which forces the bouncing or return characteristics of the various wavelengths. Okay. All right. So the green. We talk about the at rest, the elastic of the environment, the elastic of this deep blue. So that's one of in the isolating cavity between the ionosphere and the Earth. All right, that's the insulating cavity. All right, you have a there's a space there that is that at rest state of the environment. So normally speaking, that at rest state will act as a elastic, pushing against the influences coming from outside, and it wants to stay, the Earth, the insulating cavity wants to stay at rest at fair weather. It's not until we get in the solar weather that kind of bumps things down to us that it kind of goes into action to right itself to get back to the at rest state. So part of what we have with Schumann resonances are they're that are bouncing against the tendency to want to go back to rest from the environment. Okay? Does that make sense? If that makes sense to you, please leave a comment. Yes, that makes sense. If it doesn't, please leave a comment. I don't know what you're talking about. I'm lost, and I will try and pick it up. Okay. And in all things, if I say make a comment that you don't understand, please, you got to make it a point to me to say, I don't understand this, rather than not say anything to me, give me a chance, and then go tell someone else that I'm full of crap or I talk way over people's heads, right? The only way I talk over your head is if you don't let me know that I've lost you, okay? I'm not assuming everyone watching this is a beginner. There are people who've been around for a while. They know this material, and this is advanced stuff. Okay, I have a range of people that want the very first day one stuff, and then there's people that are ready for even more advanced stuff than this. So I try and hit it somewhere in the middle. I'm not going to make it. You need to help me. You need to do your part and let me know I'm way over your head. Otherwise, I don't know. I don't know. I'm not a mind reader. I'm literally not a mind reader, and I'm not planning to be. I don't know how to be a mind reader. You have to let me know you didn't get the important thing, and allow me a chance to readdress what I didn't make clear the first time. Okay, I think that's only fair, and I think that's really a the the best way for you to learn is if you didn't get it from when I said it. I mean, I'm not speaking complicated words. I'm going by the text and what the text says, and yes, some of this is complicated, but my job is to break it down to you. So if I haven't broken it down to you, I haven't done my job, and you need to let me know so that I can clarify this. Okay, there's a lot of technical stuff here, and I do my best, but quite honestly, it's beyond most people. There's not a better way to put it. So if you don't want this to be beyond you, please let me know, make comments, share, and ask. I make myself available in the comments somewhere as my email. I do the live streams, which is probably going to be what this is. After I'm done recording this, I'm probably going to put it out as a premiere and do it as a live stream so that I can have comments on that. And so that's why I do that. That's why I'm posting on Facebook. That's why I post on YouTube. That's why I make a live stream, is so that I have the ability there for people that you can ask me comments one-on-one, and I will do my best to clarify this or provide maybe more information that makes it a little bit more clear. Okay, but please, if I haven't made it clear about this, it's not because I need to make this complicated. I don't want to make this complicated. If I've made it too complicated that you're not getting something out of it, I haven't done my job. And my job here is not to boost my ego with some BS. My job here is to make this as clear to your understanding as possible. And if I haven't done that, I failed at my job. All right. So I just want to say that. I just want to make that clear almost an hour into this, that if you haven't understood that, if you don't understand that, if you followed along at this point, that's great. If you have hung on this point and you're lost, please leave me comments again. Please leave me comments so that I can readdress what I've said and maybe hopefully make it clear. Or maybe I'll make a part 2 and I will clarify just that particular part and make it a little easier to understand. The modes are not the easiest part of this to understand. Let's just say that. On doing the modes, I kind of dread this. I know what the information is, but I dread this because it is so complicated to explain what the colors mean on the Schumann charts. Okay, but once we go through it and we look at this, you'll do much better, right? And me going through all of this writing, the crappy, shitty writing that I do, it's to help you understand this better. And that's all I'm doing this for, is to help you understand better. Okay. So the where I was at with the at rest state of the environment, it always wants to go back to that. So whenever something comes in from top down or from bottom up, okay, earthquakes, okay, bottom up. Earthquakes are a great example. Earthquakes show up on the Schumann resonance. Okay, so it's important to know what you're looking at, and it's important to know that, if you follow along with it, with the what you're looking at, and you've been looking at it long enough, you should be able to start seeing some of the stuff coming in from top down or bottom up. All right, and it's important to know what's the difference. Top down is amplitude, bottom up is the magnetics, or it could be an earthquake or something else in the earth. But that's what, the Schumann resonances are there. They show you, the charts can show you either or. If you're, depending on where it's based on, depending on whatever, you'll be able to pick up, earthquakes or high amplitude, the sun, high solar days. All right, so because green is high in magnetic content, green-based colors are going to be more magnetic and display horizontally to reflect the orientation of the reporting dependencies, like quality or amplitude. All right. Quality Okay, like quality. All right. We see an upright or vertical signal in. Okay, there. All right. All right. I know what I did. All right. All right. So, all right. So with the amplitude. All right. With the amplitude, I said this already. I'm going to say it again. With the amplitude, you get these upright spikes. That indicates amplitude. So if you're looking at the wavelength here, these ones here, these spikes of amplitude, these are spikes, no questions about it, upright spikes, like pillars, okay? So these are amplitude. Now, the quality, Q, Q, are horizontal. So even though here on this, you look at it and you see it's a horizontal peak, that does not mean that it is, you're going to see this, again, quality, you got to look at quality. This is not going to show up as a peak, as a vertical peak, because it's quality, it's magnetics. This is going to show up as part of the harmonic magnetic band in there, okay? And again, once again, you have, why are you not seeing a white, you see this white mode here, why are you not seeing a white, like a Twinkie? Why aren't you seeing the creamy center of that harmonic band? Because this is a low number, 8.3. That's nothing. As opposed to 17, and then here, actually, look at this here. All right, so this right here is 14, mark of 14 here. Okay, at the same place, this is 5 or 6. So the intensity of this signal is 1/3 of the intensity of the white is approximately 1/3 of this red. And it's approximately half of, all right, so where is this? The peak. All right, so this is 7, let's just call this 8, that peak 7.4. All right, so this is like 7.4, maybe 8, somewhere around here. That's his peak here. Okay, and where was this here? This is like 6, all right? 5 or 6, all right. So this doesn't even reach 6. This reaches 7, almost 8. This reaches like 20 right here, okay? So that's why in the middle of this Twinkie shaped thing here, it's orange and rust color, is because this value together is well over 5 times what this white value is here. Even at this peak, even with the peak here, this peak still is only going up to 8.3, whereas at that point, this is at 7, okay? That's 7 right there. It's a little under 7, right? All right, maybe you see this better. All right. So you see the numbers. All right. I can't show you both numbers in there and make it on the big screen. So again, so you just have to look at it. I'm even though I'm going over this multiple times and I think you may have it, I still want to make sure that you understand why you're not getting a white in the middle of this. You get a white spike here, sure, but you're seeing this white spike here. How come there's no white in the middle of your harmonic? It's because this absolute value here, this number value, 8.3, is well, even not height, the peak right there is well below this value here. The highest it went to is 8. This here is starting at 8, right? Can you understand that? Does that make sense to you? This peak here in the magnetics, this is quality, is 8. It peaks out at 8. All right, 8.3, so just above 8. And this one here at the same place, do you see it? The same place is 7.4. All right, this is nothing. This is a little tiny spike, peak. This little blip here is approximate in size to this. All right, are you getting that? Yeah, this tiny little peak here is approximately the same numerical value as this big, tall peak here. All right, so you got to look at these numbers to tell you what the colors mean. Why are you getting, you see, again, a speak here, a spike and a peak, and there's no white there, even though you say, oh, well, it's white, it's peaking. It's not. It's not. This is the quality, this is the magnetics, and this spike is going that way, all right? So it should be going the long way, and even the height of it, again, this is a magnetic wave, so even the height of it is somewhere near where this is starting out. So this height of 8 is approximately the ground level of this here. The ground is 5 here, all right? So halfway up on this chart here, you get a 5. It's not really halfway, but you know, it starts at 4.7, and then it goes to like 5 here. 5.9, so 6. So approximately 6 is approximately halfway through the chart, whereas 6 is just down here. It's between 5 and 6. Do you see that? Halfway between the bottom and the top is like 6.14. Okay. Halfway in the white mode of the quality 1, Q1, halfway up the chart gets you 6.4, 6.2, somewhere around there. All right, you see that between the two of them? If we go over to the next one down, 6 is right there. 6.1 is not, that's not even 7.4. So halfway between these two, approximately 1 square into it, is half of the other chart. Okay, this is the quality part of it. This is why knowing the direction of the propagation is really important when you're talking about the modes. The modes are either tall and narrow or short and fat. Okay, and those are the different size and shape brushes that you have to use to paint the picture. Okay, so I've gone on to this. Hopefully I haven't tripped over myself in explaining this. Hopefully I've done a good job of showing you where this is equal to this over here, okay, and why these magnetic lines do not often appear other than green, maroon with some rust in it. You're not generally going to see white lines coming across horizontal because of the size and the shape of the waves, the magnetic waves that are bouncing around the globe. And so this is why you're getting the green and the rust color, because you look at the size, the 31. All right, look at this, 31. These are very powerful, strong waves. They're very, they're big, and that's what these are. And the kilometer scale, that's what the frequency here is telling you, is this is the size of these waves. 26.5 kilometers. And in fact, I'm thinking it may not even be 26, it may be like 265. They may have moved the decimal place over, and you need to understand that this is not like this. These are not, the lowest frequency waves are not 26 kilometers. They are closer to 2 million kilometers. 200,000 kilometers. All right, so this is what we're talking about. The low frequency waves are closer to 3 million kilometers in wavelength, okay? So these very much there may be a decimal. I'm still figuring a lot of this out, okay? So there may be a decimal place that is involved that you're not seeing in here. This may be closer to 2,650. All right, and they're doing it this way because they can't, give you a decimal. They have to do the decimal in the middle there. I don't know how it's laid out, but I'm thinking these waves are not actually 26 kilometers. I think they're closer to like 2,000 kilometers. Okay, because these are the lowest. Again, these are radio frequencies. These are the lowest of the low frequencies that you can measure. So the 3 hertz. 3 hertz is a 100,000 kilometer wavelength, if I'm not mistaken, if I remember correctly. 3 hertz is a 100,000 kilometer wavelength signal. That's 1,000,000 kilometers, right? I'm just giving you, this isn't point for point exactly correct, but I'm giving you an analogy so you can understand of the size that we're talking about. The lowest frequency waves are like millions of kilometers in wavelength, all right? So I just want to understand that. I want you to understand that. All right. All right. So we're talking about the modes. All right. So we see the upright as the vertical signal in the quality, but this is not a amplitude frequency. This is not an amplitude intensity. This is a frequency, a magnetic frequency. So this peak down here that I'm circling, even though it shows as a peak, it's still magnetics and it's not an amplitude. All right. So this is the strength of the magnetic field. This is not the vertical component of it. Please remember that. This is picoteslas. This is picoteslas, which are measuring the magnetic side, magnetic flux of the signal. Quality is magnetic flux of the signal. Okay. The colors such as teal, aqua, turquoise, and indiglo. I've mentioned indiglo. So you can see in here teal, turquoisey kind of colors, green variants are not actually in the green family. So, all right. So some of this, all right, how do I say this is complicated? All right. So some of this, all right, let me just not even talk about the green, but the indiglo here is not a product of the modes. It's a product of the background. So the indiglo, the blue, the indiglo, and some of the aqua coloring comes from an interaction with the background of mode 1 of the white color. All right. So the indiglo color that you're getting here surrounding the green, I'll put it this way. This is all the activity of the environment kind of saying, bring it on, right? We're fluctuating, we're moving, we've gone from our stasis state. So this is the as I understand it, this is the environment that's active. It's not stormy, but there's just something, there's you can feel that electricity in the air. I think that's kind of the best way to put that. That it's not an actual Schumann resonance per se, it's not an amplitude spike, but it's the background magnetics of the atmosphere. That's the way I look at it. That this sort of is telling you that there's something going on, but there's nothing specific. You can't. There's no rating for this aqua. I'm sorry. There's no rating for this indiglo. It's just a. How do I say this? It's a numerical offset from the background. So you have the background is normally dark blue. So you have these kind of activity going on. I don't know how to explain it. The like an electric, so background magnetics, background electronics, electrics. All right, I think that may be the best way to describe it. So the product of the all right. So this indiglo comes from there being some existing stuff in the atmosphere, and it doesn't even necessarily have to be this mode 1. It can be coming from the bottom up. Okay, so there's a lot of the chart itself has activity, the green, the orange, and all that. Okay, so there's a lot of activity with that, but there's also more in the background that doesn't get quantified, but it is there to be seen, like a hazy day. I think. I think that's kind of the best way to look at it. That's sort of how I look at this, like a foggy day, where you can't see through it, but you do see shapes in the background. And it's not until you get up closer to something that you see the shape and the definition of it. But on a foggy day, there's a layer of fog all over everything. But when you get close enough to something that's a bright color, you will see the shape of it. Right. And I think that's the best way to put it. That as it gets closer to a signal that it can measure, then you'll get the green or the spikes or whatever. But until it gets a measurable signal, you have just this indiglo that lets you know it's picking up something. Okay. And even if there wasn't anything else on the chart, just by it kind of having turned on, I'm thinking you would get this indiglo color, although I have a hard time kind of proving that. But I think the indiglo comes really after they turn the machine on and they measure, it's the background something in the atmosphere, right? Because the atmosphere is not at rest. Most times the atmosphere is not at rest. Most times there's something going on. All right. So even and especially in the sun during the daytime, there's always something going on. You're always finding, that like it's very active. So that's part of one of the things that it's showing you is it kind of dips down here as the day goes on, it starts getting this kind of background uh, the at rest state, the dark blue, starts coming back into the picture, but there's never a point during the day where it just goes all to dark blue. If it did, that would be the flat line, and that would tell me something, something's up, something's broken, and it may just be the machines that's broken. All right, so white and yellow is top coming down, as it were, into an otherwise calm background at rest state of the dark blue. Going upwards from rest into the bottom of the modes due to heavy magnetics, the coloration goes from dark blue into green. So you see the green. So it's basically you're going from the at-rest state into the green of these, the modes, where you start getting into the magnetic portion. So you're moving from top down or bottom up. So you will have there's nothing lower than this. There's no color lower than the green. So that's where you're seeing the greens down there at a lower kind of hertz rating, the lower frequency rating, is because it's the lowest, it's moving bottom up. Okay, so the lowest waves that you get are these, the biggest waves, the biggest, lowest waves you get are these green ones and the red ones. But you see there's not much going on with the red, but there's a lot going on with the green here. So the green is going to be generally the magnetics, the magnetic portion of the program screaming across like that, bing, 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 bing. And you will get a lot of green in the magnetics and not so much green in the amplitude portion. The amplitude portion, high charge, moves top down, so you'll see a lot of the spikes are in white because they're high charge. But if they picked another color, if they pick yellow for mode 1, this would not be white, it would be yellow. Just understand that. If the two of them were reversed, if it was yellow and then white, these would be peaks of yellow and not white. Just let's understand that. Okay? Okay, I'm almost done with my notes here. The white and the yellow is, I think I said that, the white and yellow are top down, top going down, as it were, into an otherwise calm background state of the at-rest dark blue. So, what am I saying here? All right, so the yellow, you'll see generally the yellow and white, spikes of yellow and white are top down, and you're not seeing the white horizontals because the amplitude is the strongest coming down, the way that the mode is, that it's the strongest signal is coming top down. And so that's why the amplitude, the mode 1 and mode 2 of the amplitude are picking that up, and you will see the strong incoming intense signals from the ionosphere are the colors of the white and the yellow because, again, because the amplitude mode 1 measures the strongest and tallest part of the signal. Okay? Going upwards from rest, from the zero state, from at rest, into the bottom of the modes due to heavy magnetics or due to an earthquake, something like that. The coloration goes from dark blue into green, which is mode 4. This is how we know that the bright teal and turquoise is a signal moving from top down, instead of moving, oh, whatever. All right. So the dark blue would be going from, or I'm sorry, the dark green is what's going from blue, the dark blue, into green. You don't get a light blue or a turquoise going from dark blue to green. Okay, that's what I'm saying here. That in order to get the turquoise colors, you have to move from blue to white, yellow, in that way. So that's how you know that a lot of this is amplitude. It's not magnetics per se, because it's the whitish color. It's before you get to a color. It's before you get to a specific color, like the white or the yellow, the orange. I say specific colors. I mean the green, the rust, these kind of things. The indiglow is a background state that's not particularly a color. Dark blue is not a color. Indiglow is not a color. The colors are green. You start getting into a teal, a coherent shape. That's where we start getting into the colors. I think that's a good way to put it. So that's, again, why is it important to know the color? Because your four primary colors. If it's not one of those and it's a shade of blue, what is that telling you? Okay. And I've gone through this. I'm not going to tell you. If you haven't followed along, go back from the beginning, but that should tell you what you're looking at is top down or bottom up. All right. Red and yellow make orange, pumpkin, rust. When mixed together with the white, we get coral or pink. These indicate, not really a pink, the variant of coral or orange. Salmon. It's not really coral. It's not pink. It's salmon. These indicate mid-grade electrics, fairly balanced with magnetics. This is why orange and rust colors seem to float in the air of the chart, because they are floating. They literally are floating in the middle of this cloud of magnetics. Okay. All right, so that's all I got in my notes. This video is going to wind up being almost 2 hours long, explaining the modes, and this is a fairly in-depth, this is more in-depth than any one of the other videos I've made before, talking about the modes. Okay, and so I think what I'm going to do is I'm going to do the same thing I did last time, have this as a live stream, play it as a movie, and that way I can be present with the comments for everyone. All right, and that's really important. I need to be part of the comments. All right. So, all right. So that's it for this video. I'm going to close it now. I'm going to close it now. Saving this. I already posted it on the WordPress blog, and so I'm making a link to that entry. There should be one. Actually, did I put it up here? Yeah, the WordPress link here. All right. So as you see, so the WordPress link is here. So I've already put this onto the so you can see the text of this, and I sometimes will post it on WordPress and add more stuff to it, and it all's got to be edited as well. All right. So, all right. So that's it for today. Thank you all for being here. Thank you all for coming here to the to my channel and to listen to what I got to say. This long ass video. And what else? So I will be putting this online shortly, and like I said, I'm probably going to do it as probably not a premiere, but probably as a live video, and I'll give me a chance to chat with people. Either way, thank you all for being here. I appreciate everyone coming today, for your love and support and comments. I need you all to be here with me. Otherwise, I have nothing going on in my life, really. There's not really any other reason for me to be here if I'm not doing the Schumann. And it's just that simple. I don't care to be here if I'm not, right? I mean, I've already lived enough. I've done enough. I've seen enough. So I need your feedback and your comments to give me some reason for being here. It may sound depressing to you, but if all your family was gone and all of your friends had gone, you would think differently as well. I guarantee that. If all of your family was gone, they all had passed away, and you were just living here by yourself, you would think differently about your whole life and everything as well. I guarantee that. And if all your family is here, just be grateful. However your condition with them is, be grateful you have a family. Be grateful you still have people that are there for you, because they can go away. And that is something that can and does happen. So on that really cheery note, thank you all for being here today. I'm going to play this on the outro, and I will talk with you shortly. Thank you. Thank you, everyone. Have a good rest of your night. Here, and I will see you in comments and see you on the live stream. Thank you all. You're wonderful people. I very much appreciate that. And among all things, if you're going to do it properly. Thank you, everyone. Have a good rest of your night. Bye-bye.
To every man, woman, boy, and girl, you came out here to have some fun, but let's do it in unity, and let's do it as one. House music is a universal feeling that we all have deep down in our soul, and it's time to release it. It's time to lose total control. And the only way to do it is to do it properly.
I wanna be president.
isolation.